Morenci, Arizona. 1998. The industry consensus was settled. The electric drive haul truck had won. Unit Rig and Komatsu had proven that pushing anything over 240 tons up an 8% grade required a diesel engine turning a generator, powering electric wheel motors. Mechanical transmissions, with their drive shafts, torque converters, and shifting gears, were considered obsolete for ultra-class payloads. But on the steep, rocky ramps of the Morenci copper pit, a new silhouette emerged through the Arizona dust that defied the entire engineering consensus of the mining industry. This was the Caterpillar 797. It carried an unprecedented, staggering payload rating of 360 tons. It was the largest two-axle vehicle ever constructed in human history. And beneath its towering deck plate, there were no electrical cables and no traction motors. Caterpillar had stubbornly refused to concede the ultra-class market to electric drives. Instead, they scaled up the traditional mechanical powertrain to terrifying, unprecedented dimensions. The sheer audacity of the design shocked mine planners. Pushing over 1 million pounds of gross machine operating weight up an 8% grade using rotating steel shafts and interlocking gears seemed like a recipe for catastrophic mechanical failure. The kinetic forces involved threatened to shear traditional planetary gears into shrapnel. How did Caterpillar engineers generate enough raw mechanical horsepower to move a 360-ton payload without shattering the driveshaft the moment the operator engaged the throttle on a steep incline? To move a gross operating weight of 1,375,000 pounds, Caterpillar needed an engine that did not exist in the earth-moving catalog. A single diesel block capable of producing over 3,000 horsepower would have been too large to fit between the frame rails of a haul truck. Caterpillar engineers solved this by taking two massive 12-cylinder 3512B diesel engines and physically coupling them together end to end. This created a colossal 24-cylinder power plant producing 3,400 horsepower. But linking two independent V12 engines to act as a single prime mover introduced a severe mechanical synchronization problem. If the front engine revved even slightly out of phase with the rear engine, the resulting torsional vibration would tear the connecting crankshaft apart. The engines were synchronized by a master electronic control module that monitored fuel injection timing down to the millisecond, forcing the twin blocks to behave as one unified heart. This massive power plant did not send its energy to a generator. It sent it directly into a gargantuan torque converter. The torque converter had to absorb the brutal twisting force of 3,400 horsepower and transfer it back to a 7-speed planetary power shift transmission located midway down the chassis. Before we go further, if this kind of content is what you have been looking for, subscribe to the channel. Understanding Caterpillar's refusal to abandon mechanical drivetrains reveals the intense engineering rivalry that defined the modern ultra-class mining truck. And leave a comment. If you turned wrenches on those early Cat 797s, what was the most frequent failure point you saw on the massive rear differentials before the cooling lines were upgraded? In a future video, we will examine the Komatsu 930E and how its AC electric drive system fought back against Caterpillar's mechanical supremacy. How did a transmission physically shift gears under the relentless, crushing load of 360 tons on an 8% grade without snapping the teeth off the clutch packs? The transmission of the Caterpillar 797 was a marvel of brute force engineering. It was a 7-speed planetary power shift, physically larger than a pickup truck, bolted securely within the heavy steel frame rails. In a standard passenger vehicle, shifting gears under a heavy load causes a momentary drop in momentum. On an 8% ramp in the Morenci pit, a momentary drop in momentum while carrying 360 tons of copper ore meant the truck would stall and gravity would instantly pull 1 million pounds backward down the mountain. To prevent this, the transmission utilized an electronic clutch pressure control system. When the truck approached the top of a gear ratio, the transmission did not simply release one clutch pack and engage the next. Instead, it carefully modulated the hydraulic pressure, slipping the outgoing clutch while simultaneously slipping the incoming clutch. This allowed the transmission to shift seamlessly under full power without ever breaking the flow of torque to the rear wheels. The transition of power was uninterrupted. However, the physical reality of forcing thousands of horsepower through steel clutch plates generated immense friction and extreme heat. The transmission oil had to be continuously pumped through a massive array of coolers mounted on the front of the truck. Despite the sophisticated electronic controls, the veteran operators driving the 797 could still feel the raw mechanical shockwave of the shift echoing up through the cab pedestal. How did the operators, accustomed to the smooth, gearless acceleration of electric drive trucks like the Lectra Hall, adjust their driving style to manage the violent, rhythmic shifting of the world's largest mechanical powertrain? Operating the Caterpillar 797 required a completely different sensory integration than driving an electric wheel truck. In a diesel-electric machine, the operator pressed a rheostat throttle, and the electric motors provided a smooth, continuous surge of power from 0 to top speed. The driver simply watched the ammeter to ensure the motors did not overheat. The 797, however, was a profoundly mechanical experience. The veteran operator had to constantly read the tachometer, anticipating the shift points based on the engine RPM and the grade of the haul road. If the truck hit a soft patch of mud or a steeper section of the ramp just as the transmission initiated an upshift, the engine would lug down heavily, sending a deep, shuddering groan through the entire chassis. The operator learned to drive the tach, slightly feathering the throttle or manually holding the transmission in a lower gear to maintain the engine exactly in its peak torque band, around 1,700 RPM. It required acute physical awareness of the machine's momentum. The operator felt the interlocking gears, the hydraulic pressure of the clutch packs, and the immense tension on the carbon fiber driveshaft connecting the transmission to the rear differential. They were managing the sheer physical stress of the machine through the soles of their boots, but hauling 360 tons up the high wall was only half the equation. When the truck dumped its load and turned back toward the pit floor, how did the operator safely decelerate 1 million pounds of gross vehicle weight down an 8% grade without burning the mechanical brakes to ash? Decelerating 1 million pounds of gross machine weight down an 8% grade without dynamic electric braking required a massive hydraulic engineering solution. On a diesel-electric truck, the wheel motors become generators during descent, creating magnetic resistance that creates retarding force, with the resulting heat dissipated through massive grid resistors on the deck. The 797 had no grids. Instead, it relied on a sophisticated integration of the engine's compression brake and gargantuan, oil-cooled multi-disc brakes on all four wheels. These brakes were not exposed to the air. They were completely sealed within the wheel hubs, bathed continuously in a high-velocity flow of cooling oil. To maximize retarding force, the transmission would shift into lockup, creating a direct mechanical link from the wheels back to the engine. The engine ECM utilized variable valve timing on the twin blocks to create retarding torque, effectively turning the 3,400 horsepower heart into a gargantuan air compressor holding back the momentum. The operator managed the descent using the automatic retarder control, or ARC, which modulated hydraulic pressure to the sealed brakes to maintain a constant downhill speed, ensuring the brake oil temperature remained within the critical operating window. The veteran operators could identify the specific, high-pitched whine of the retarding oil pumps over the roar of the V24 engine. It was the sound of 3,000 horsepower of kinetic energy being converted into hydraulic heat and pumped away to the front cooling core. But once the truck arrived at the loading face, how did the massive turning radius of the world's largest mechanical truck redefine the geometry of the shovel-matching sequence? A 360-ton truck meant nothing to the mine economics if it could not be loaded efficiently. The arrival of the Caterpillar 797 at southwestern copper pits, like Morenci, fundamentally forced a systemic upgrade of the primary loading tools. To achieve a critical 4-pass loading match, the mines had to introduce ultra-class electric rope shovels, specifically machines like the P and H 4100 series, carrying dippers with capacities exceeding 60 cubic yards. This was the final optimization of the 20th century haul cycle, matching the world's largest mechanical truck to the world's largest electric shovel. The interaction demanded extreme operator precision on both ends. Shovel runners, accustomed to loading 240-ton trucks in 3 or 4 passes, now had to perfectly center 24-cylinder engines beneath a 60-cubic-yard dipper, managing the structural swing inertia to avoid devastating dipper-to-body contact. For the CAT 797 operator, the primary challenge was spotting the towering truck within the correct swing radius of the shovel while navigating the massive turning circle of the mechanical chassis. The sheer physical footprint of the 797 required the shovel face to be established with far wider, stable benches to allow the truck to execute the loading turn without risking the berm or the high wall. Production engineers had to redesign the entire pit geometry to accommodate the giant's mobility. But as these giant mechanical powertrains began accumulating thousands of hours on the high production shifts, the unrelenting physical force required to move 1 million pounds created a different kind of crisis in the maintenance bays. What happened to the mechanical components when the brutal forces on the high wall finally rivaled the structural integrity of the steel and rubber that contained them? Moving 1 million pounds of gross weight with a mechanical drivetrain meant that the ultimate bottleneck of kinetic force occurred at the rear axle. The carbon fiber driveshaft transferred the immense torque from the transmission into a colossal rear differential, which then split the power to the final planetary drives housed within the rear wheel hubs. In an electric truck, the wheel motor is a solid-state rotor with few moving parts. The CAT 797's final drive was a dense, heavy cluster of massive steel sun gears, planet gears, and ring gears. When the truck hit an 8% grade fully loaded, the tooth-to-tooth pressure inside those planetary sets reached the absolute metallurgical limits of forged steel. The physical strain was immense. If an operator allowed the rear tires to slip on wet Arizona bedrock and suddenly catch traction, the resulting shock wave would travel instantly up the axle and shatter the planetary carriers into jagged shrapnel. The veteran operator could not rely on automated slip control software. They had to feel the mechanical grip of the tires through the chassis. They learned to apply the throttle with agonizing smoothness, keeping the massive twin V12 engines precisely within the torque curve without overpowering the traction limit of the rubber. It was an exercise in extreme mechanical empathy, but transferring 3,400 horsepower through interlocking steel gears generates something far more insidious than sheer mechanical stress. How did Caterpillar engineers prevent the massive rear axle housing from melting itself from the inside out under the intense friction of the haul cycle? The friction generated by the rear differential and the planetary gear sets created an immense thermal load. The heavy gear oil inside the axle housing could easily boil under the continuous strain of a long uphill haul at Morenci. To prevent catastrophic metallurgical failure, the 797 utilized a massive, dedicated rear axle cooling circuit. High-volume pumps continuously cycled hundreds of gallons of oil from the axle, running it through external heat exchangers before forcing it back into the gear sets. The front of the Cat 797 was dominated by a towering radiator block. This immense structure was not just for cooling the twin V12 engines. It was designed to shed the accumulated heat of the 7-speed transmission, the torque converter, the retarding brakes, and the rear axle differential. The truck was effectively a rolling thermal management plant. The veteran operator constantly scanned a specific bank of digital temperature gauges on the right side of the console. They knew that if a rear axle cooling pump failed while hauling a full load, the planetary gears would superheat and fuse together within minutes, locking the rear wheels and dragging the massive truck to a violent, shuddering halt on the ramp. But all of this mechanical engineering, the twin V12 engines, the transmission, the massive cooling arrays, and the heavy differential added an immense amount of empty vehicle weight. How did the mining industry physically support a truck that weighed over 600,000 pounds before a single rock was dropped into its bed? The empty weight of the Caterpillar 797 was a massive engineering penalty. The sheer mass of the mechanical drivetrain, the twin engines, the transmission, the heavy steel driveshafts, and the colossal differential meant the truck weighed significantly more than a comparable electric drive unit. To carry this extreme dead weight plus 360 tons of payload, the truck required a tire that did not exist. Caterpillar partnered with Michelin to develop the 5980 R63 radial. These tires stood 13 feet tall and weighed over 11,000 pounds each. But rubber is a thermal insulator. When an operator navigated a fully loaded 797 through a sweeping turn on the haul road, the lateral friction generated immense internal heat within the massive tire blocks. Because of the incredible gross weight of the mechanical truck, this heat built up faster than the rubber could dissipate it to the air. If the operator drove too fast through corners or exceeded the recommended speed on the flat, the internal temperature of the tire exceeded its vulcanization point, causing the heavy steel belts to separate from the rubber in a catastrophic thermal blowout. The mine dispatcher tracked a vital metric known as ton-miles per hour, or TMPH. The veteran operators knew they could not simply race the truck. They had to maintain a strict, agonizingly paced rhythm on the haul road, managing their cornering speeds to preserve the most expensive consumable item on the mine site. The truck had the horsepower to run faster, but the tires dictated the pace. The 797 pushed mechanical engineering, tire chemistry, and operator endurance to their absolute breaking points. When the first generation of these mechanical giants finally reached the end of their operational lifespans, what had they proven to the electric drive monopoly? The original Caterpillar 797 proved that mechanical drives could survive the ultra-class payload barrier. It defied the industry consensus and forced competitors like Komatsu and Liebherr to aggressively innovate their AC electric drives to compete with Caterpillar's sheer mechanical torque. The early 797s at Morenci and other major open pits were eventually replaced by newer, refined iterations, their massive twin engines and planetary transmissions worn out from moving millions of tons of copper ore. What the operating logs showed about how they were managed, how the veteran operators listened to the lugging of the twin V12s to time their shifts, how they feathered the throttle to protect the planetary gears, how they managed their cornering speed to prevent catastrophic thermal blowout of the tires, went with the operators when they retired. Some of it was written down, in the form of informal shift notes and maintenance observations that someone thought to keep. Most of it wasn't. If this video gave you something real, subscribe. More machines, more minds, more of the operational reality that the trade show brochures never contained. Understanding the audacity of the original 797 is essential to documenting the intense engineering rivalry that built the modern Hall fleet. And if you ran one of these trucks, worked on one of these shovels, or engineered one of these operations, tell us in the comments. If you operated an original 797, what did the transmission shift actually feel like through the floorboards when climbing an 8% grade? The most complete operating manual for these machines is in the heads of the people who ran them. Most of it was never written down. The ramp is still there. The grade is still 8.5%. The trucks that run it now are entirely automated and know nothing about what was learned on it.